Hello, this presentation is on the life cycle costs of galvanized steel girder bridges. My name is Michael Barker. I'm a professor of civil and architectural engineering at the University of Wyoming, and I'm also the director of education for the Short Span Steel Bridge Alliance. Today's presentation is going to cover two main topics. First, the life cycle cost comparison of steel versus concrete bridges, and then we're going to get into the life cycle costs of galvanized bridges. But first, of course, we look at initial costs for steel and concrete when we're comparing those two materials for our bridge needs. And the Alliance has conducted many case studies where we compare county and state bridges, where we look at actual bids and actual costs across the United States. And what these studies show is that steel and concrete bridges are competitive on initial costs, and that owners should consider both materials when selecting the right bridge for the bridge need. But what about life cycle costs? As owners replace their bridge infrastructure, the question of life cycle costs, or life service and life cycle costs, routinely comes up between concrete and steel bridge options. And the bridge industry did not have a good answer until now. Both the steel industry and the concrete industry claim an advantage when it comes to life cycle costs using anecdotal information. And that is just not very convincing. So a study was conducted on bridges in Pennsylvania to examine the historical life service, or performance and maintenance, and agency life cycle costs, or the true agency costs for a bridge. And the historical aspect was used to look at what actually happened instead of the guesswork for anecdotal information. Now, the full report can be found on shortspansteelbridges.org website, and we certainly want to thank PennDOT for participating in the study. So to do a life cycle cost analysis, we have to start with a comprehensive inventory of bridges where we know the initial costs and date built, all the maintenance costs and date performed. And then we need an end of service date or an end of life model so that we can lay out the life cycle to do the analyses. The purpose of the study was to look at typical modern bridges, and those were decided to be precast I-beam bridges, box bridges where the boxes were adjacent, and boxes where the boxes were spread out. And then compare those to steel rolled shape and welded plate girder bridges. And the modern part comes with bridges built between 1960 and the year 2010, where precast concrete became a mainstream material method, and modern detailing steel bridges started. Then, of course, these bridges had to have complete and accurate department maintenance records. They had to have known initial costs, and, of course, complete and accurate external contractor maintenance and rehabilitation costs. So PennDOT has over 25,000 bridges in their bridge inventory. Of those, 8,500 of them are of the 5 types. And of those 5 types and those 8,500, over 6,500 were built between 1960 and 2010. And this table shows how many bridges were considered for the database that met all the criteria, which means that we had all of the information that we required for the life cycle cost analysis. Now, of course, these bridges are still in service, so a bridge life model needed to be developed, and it was based on deterioration rates, not of the bridges that made the study, but of all the 8,500 bridges. A deterioration rate was calculated based on what superstructure condition rating was in the year 2014, assuming it started at a 9, and then divided by the number of years that had been in service. Then a remaining life could be calculated by assuming the bridge was replaced at a structure condition rating of 3 and figuring out the total bridge life as being the addition of those two. This table shows the deterioration rates for the 5 different types of bridges, and as we can see, they don't vary very much. And a deterioration rate is a condition rating loss per year. So they're in the 7 to 8% range. So taking all that information, Excel files were produced where the first file talked about location, year built, spans, length, area, geometry, materials. Then a second file with all the department and contractor maintenance performed on those bridges. And then a results file that recorded the initial costs and the perpetual present value, or the capitalized costs, and the future maintenance costs in the present value format. And then those bridges can be compared to each other. Now, the report does a lot of variable work. We're only going to look at a couple of them here. We're going to start with bridge life, and then we're going to look at bridges with a length up to 140 feet, which is the definition of a short span bridge for the Short Span Steel Bridge Alliance. Of course, the full report can be found on shortspansteelbridges.org. And after this report was completed, an additional life cycle cost study was done on galvanizing, and today I will be reporting on the results of that. So looking at bridge life for all the bridges, we see that, again, there's not a lot of difference in the right column here, where it ranges between 74 years and a little bit over 80 years for the 5 types of bridges. So there's not a lot of difference in expected bridge life for the 5 types of bridges. Here's where we see the capitalized costs, or what we call the perpetual present value costs. We see that in that first highlighted column there under capitalized costs, and we see, and this is for the bridge lengths up to 140 feet. And we see that 4 of them are pretty close to each other. One of them is a little bit higher, steel girder bridges, but we do understand that because they're not that economical below about 60, 70 feet. Also reported here are initial costs, the present value of all future costs, and again, the average bridge life for those bridges that are up to 140 feet in length. And so this initial study, the objective was to see, is there one that performs better than another of these types of bridges? Is it a precast box when they're adjacent or when they're spread? Is it a precast I-beam? Is it a steel rolled beam, or is it a steel plate girder? And here are the kind of results of that initial study, with a statement at top that say, all are similar with none way out of balance. And we saw that with bridge life, and we saw that with capitalized costs, and we saw that with initial costs and things like that. If we look at the results for all of the bridges, the overall weighted average capitalized cost is a little over $252 per square foot. And all the bridge types averages were within 14% of that. Now, understanding that the standard deviation range within those types range between $48 and $65 per square foot, or a coefficient of variation between 20 and 25%, the conclusion can be that any one type of bridge may be the most economical for a given bridge project. There is no one type of bridge that clearly beats the others. And this is just a probability density function showing those averages and those dispersions for those 5 types of bridges. So the conclusions of that is that typical concrete and steel bridges are competitive on initial costs, future costs, life cycle costs, and bridge life, and that owners should consider both steel and concrete alternatives for individual bridge projects. But there were no galvanized bridges in that database. So what about galvanized steel bridges? Now, steel girder protection systems include painting, weathering steel, and galvanizing. And galvanizing has become an economical and effective protection system. The initial costs are about equal to, or can be even less than, a quality 3-coat paint system. There's a significant increase in the life of the steel bridge, and there's near zero future maintenance on that galvanized protection system. So another study was conducted, and the objective of that study was to develop useful owner information on the effects of galvanizing on the historical life cycle costs for typical bridges. And this work was sponsored by US Bridge out of Cambridge, Ohio, for some work they were trying to do in Puerto Rico. So if we think about a galvanized steel bridge life cycle compared to a painted girder, the benefits certainly are extended life and reduced future maintenance, since painted bridges usually need to have repainting performed. So on the top here is the life cycle of a painted girder, where we assume, well, what we found from the study is that it lasts about 80 years. And in that time, we have to have some sort of maintenance to take care of that protective system. The bottom here shows a galvanized girder. 2 things here. We remove the painting and we extend the life. And this study assumed that galvanizing extends the life of a galvanized girder by 25 years. So where did that 25 years come from? It comes from the American Galvanizers Association, hot dip galvanizing time to first maintenance, or some of their studies, and looking at the performance of galvanized bridges across the country. For instance, the Stearns Bayou Bridge was built in 1966. In 1997, it predicted 66 more years until the first maintenance, which would give it an expected life well over 105 years. So that's where that 25 years came from. So to that original database, the painted steel bridges in that database were modified by assuming the steel had been galvanized instead of painted when it was built. Now, there are some assumptions that have to go with that. Like I said, we assume that the galvanizing added 25 years to each bridge life, that the galvanizing costs were the same as a quality paint system, so no change in the initial costs, that future painting costs are removed from the maintenance record, and corrosion repairs to the girders are removed from the maintenance record. But all the other maintenance, concrete deck, joint repairs, other maintenance remained in the maintenance record. And so now I'll do an example. Here's an example painted steel girder bridge. It's 220 foot in length. It was built in 1973. It has a current super condition rating of 6, which means that using a deterioration rate of 7.11%, the remaining years is 42 years. So the bridge life is estimated to be 83 years total. If this thing was galvanized when it was built, we assume it's going to last 108 years. So then we bring in the costs. Up at the top half of the slide are the actual costs and the actual years of those costs were incurred at the bottom for the painted bridge and the galvanized bridge. Of course, the painted bridge has the maintenance of the repair of the girders and the galvanized does not. So using the engineering news record construction cost indices to bring those up to constant 2014 dollars, the bottom half of the slide shows what it would cost if these bridges were built and maintained starting in 2014. So these are the costs that we take into the life cycle costs. So here on the left is the painted bridge and on the right is the galvanized bridge, and we put the initial costs and the maintenance costs in here, and I agree this is a very simplified version. And from that, using a discount rate from the Office of Management and Budget of 2.3%, we can find a present value cost for that life cycle for the painted bridge of $140 per square foot and the galvanized bridge at $121.41 per square foot. And then also recorded here is the present value cost of the future maintenance for the painted bridge. But I cannot compare these two bridges directly because the outcomes are different. One lasts 83 years, one lasts 108 years. And so what we do is we assume that we replace the bridge with an identical bridge every time the life cycle runs out in perpetuity, or we get a perpetual present value cost, or what we call a capitalized cost. And we see that the painted bridge is $165 per square foot, and the galvanized bridge is just a little bit under $133 per square foot. And from that, for all the steel bridges in that original database, we can compare the painted steel versus the painted galvanized. And then I also have a row on here because some of those bridges were also weathering steel. And we see that there's a significant decrease in capitalized costs for the galvanized bridges compared to the painted bridges. And that's because of the extended life and the lack of future maintenance, or the reduction of future maintenance. And that comes out to about 8.5%. Now we can also compare to the weathering steel bridges, but we have a little bit of problem there. There were not that many weathering steel bridges in the database, and some of those weathering steel bridges are more complicated. They might be curved or they might be skewed bridges. And so we're not doing a direct comparison to weathering steel here, but we can do a direct comparison to the painted steel bridges. And so now I'm looking at only the short length bridges again. What the Short Span Steel Bridge Alliance considers short span bridges, 140 feet max, not simple span. You can see the average number of spans vary a little bit here, but these are pretty good comparisons. And I've got steel painted and or steel rolled beam painted and steel rolled beam galvanized, and then also the 3 concrete alternatives there. And we can see that galvanizing lowers capitalized costs significantly. It also lowers the present value of future maintenance costs significantly. And of course, it's got a longer life because we assumed it was 25 years more. But almost more important is the comparison to the concrete alternatives. Here we see that the steel galvanized is the lowest capitalized cost of all the 5 types of bridges shown here. Precast box spread comes in next, and then steel painted is the 3rd least capitalized cost. We also see the same type of thing with future maintenance costs and, of course, the bridge life. And so concluding this, galvanized bridges have significantly lower capitalized costs and, of course, last 25 years, according to our assumptions, compared to the painted steel bridges using rational assumptions. For all the painted bridges, galvanizing reduces capitalized costs 8.1% and 8.6% for rolled beams and plate girders, respectively. For painted bridges with that shorter length of 140 feet, galvanizing reduces capitalized costs by 8.2% for rolled beams and 9% for plate girders. And for all the painted steel bridges, galvanizing reduces present value of future costs by about 50%. The reduced capitalized costs also result in steel bridges being more competitive compared to concrete alternatives. For those shorter span steel bridges, or for those shorter span bridges, when we're using rolled beam bridges, galvanized steel is less expensive than the best concrete alternative by 6.5%. Whereas painted steel is actually a little bit more expensive than the best concrete by 1.9%. And so in summary, typical steel and concrete bridges are competitive on first costs. Typical steel and concrete bridges are competitive on life cycle costs. And when we consider galvanizing, we can say that galvanizing is economical for first costs. We can say that it extends the life of steel bridges. It reduces future maintenance costs, and it can lower agency life cycle costs. And with that, I will close out with this slide. Like I said in the beginning, I am part of the Short Span Steel Bridge Alliance. I encourage you to visit shortspansteelbridges.org, where you can find the full reports on the life cycle cost studies that I presented here, but also a lot of information on different types of steel bridges, case studies, opportunities for scheduling a workshop. And we also have what's called eSpan 140, which is a design tool where you can determine the preliminary design for a short span steel bridge in just a matter of minutes. So I encourage you to visit the shortspansteelbridges.org website. And with that, I will close out this presentation. Thank you for attending.